Let's see now the second main technique we want to present in this lecture, linear Kalman filter. So, belonging to the state estimation techniques, the goal of a linear Kalman filter is, of course, as always, to have a proper estimation of a state x, which vary, in this case, in time. So the parameter k here, x of k, represent the state varying in time. A state can be, as we've seen, a velocity of the car, the position, but can be for even a temperature or whatever quantity that we want to estimate with respect to our problem. So I think that the best approach to understand what a Kalman filter is from a sensor from fusion perspective is to understand what is the context. So what are the input elements that we have. And as we will see here, we have three main elements to use a Kalman filter. The first one is what we call the state observer. The state observer represents everything, every variable that we can measure and of the state x. Can be the state itself, as in the other case, if we remember, we wanted to estimate the constant of gravity g, which of course is something that is constant in time. We assume constant in time. But and we measure directly the acceleration itself through an accelerometer. But this can be something. I mean, in other application, the state observer can measure something which is indirectly connected to the state itself. The second element is what we call input signals. Or UDK, basically represent everything which is measured again through sensor that affect the state itself and affect the evolution of the state. The third main element, I think this is the most important here, is a model. So a model, or even called a motion model, tells how the state evolved in time with respect to the previous state and, as we said, with respect to the input variables. At the very end of the day, what we have, and I think some of you can be familiar with it, is a linear system of equation. So here we have our motion model. We tell how the state vary in time. And here we have our measurement model or state observer, as we said. We tell us how the observation on the state vary in time. So let's see the issue we want to solve with the Kalman filter. The real issue, as we said before, is the noise. And here we have two main sources of noise. The first type of noise is here on the measurement model, so on the state observer, which is represented by this variable VDK. It is random process, actually, which is usually represented as a normal distribution, but actually represent the uncertainty that we have on the measurement and due to the sensor, basically. And this is the same nature of the noise we have seen on our previous example with the estimation of the constant of gravity g. Here, of course, we have a second type of noise, which is called process noise, and represent actually the uncertainty, our ignorance on the evolution of the model itself. This is usually set as a Gaussian distribution, which the theory tells that, under this condition, the Kalman filter get the best estimation performances. Here, with the Kalman filter, we will try to cope with these two sources of noises. But let's try now to give an example. So let's imagine that we have a car which is, progressing forward on line, which is represented by this axis. What we want to know actually is the position of the car and the velocity at time k. So our state here will be, our state x will be the velocity at time k and the position at time k. The acceleration is intuitively an input, so it's something we can control. Actually, when we press the pedal, we impress a certain acceleration to our system, to our car, actually. So basically, we can write the state x has the P and dP in dt, so the position and the velocity, while our input U, the acceleration, is the second derivative of the position in time. In this case, we can see that our observer is the position, the position itself, and can be obtained, for example, from an external source like a GPS. And we will see in the next slide all the detail of how this can be possible with a Kalman filter. So our goal is to estimate the velocity and the position, and with a Kalman filter we do through three main steps. The first step is the prediction. As we see here, we have we can measure our input acceleration through a sensor, for example, an accelerometer, and we can write a model that connects the state xtk and the state k-1 through, for example, in this case, the cinematic laws. So here we have our motion model, which, as you can see, are given even by the laws of cinematic. So remember that the first step here is we have the position at time k-1, and we have the velocity, and through the application of the input of the acceleration, we calculate what is the position and velocity at time k, and this is our prediction made by the model. The second step actually is the measurement. So at time k, we take our GPS receiver and we read what is the position that our GPS tells us about the car. And so our state observer here will be represented just by a matrix 1, 0 here, because the measure, what we have taken by the GPS, is just the position. So the first entry of our state. And of course, here we have the noise. So we do the measurement, which of course has a given uncertainty. And at third step, we have the update. So we take what our model predict, we take what our sensors, I mean the GPS, our state observer tell us, and we fuse the two measurements in order to get an updated and corrected position and velocity. So as overall, we can see the Kalman filter can be represented as the scheme here below. We have a model prediction, which give us a first a priori, it's called usually estimation of the state. And then what we do, we apply on this estimation, we apply a correction given by this differentiation here, which is differentiation of the a priori state with the measurement we have done through the state observer. And this parameter kdk represent actually what we call Kalman gain. Of course, here is not a lecture on Kalman filter. The goal here was to give you a basic explanation, intuitive explanation of what is a Kalman filter and how it can be applied in our context. So I will not go further on the detail. I'm sorry for people like Matt. This was not a lecture for to give all the theoretical background on the Kalman filter. So I really hope that I've been able to provide you some good intuition that can be used, how a Kalman filter works and where a Kalman filter can be put.